All right, apparently we are recording.
Hi, Diego.
I can set this up so that my smartphone controls it turns on. I just noticed that.
I feel like this video is gonna be like an interactive video because you keep saying Diego.
Yeah,
So, like, just imagine that you are Diego, viewer.
that's right. Yes, even if you're not.
Even if you're not.
Future years you might be like, this isn't for me. I can't pay attention to this. My name is not Diego.
Or somewhere down the line, you have the other Diego.
Yes, that's right. Yes. Yes, I made a recording in case any other Diegos in the future want to use the class. Other than that, no, it's simply not happening.
It's like 10 years from now. Diego.
Yes. All right, let's see. So we had decided, I believe, that a central force conserves angular momentum by saying r cross p and all that sort of thing. Is that right?
Yes.
And then I'm looking for. And then, right, oh, right, we made a long skinny triangle. Did we make it a long skinny triangle?
Yeah,
Okay.
dA equals 1/2 r squared d theta.
D theta, right. dA is 1/2 r squared d theta. That's where we were. dA is 1/2 r squared d theta. Yes. And so it is with Diego at this point.
Wow. Oh my God. Whoa. Okay, I think that takes the cake for
Yeah.
the worst joke that's ever been said in this room.
I'll bet I can make it. That sounds like a challenge.
That is the metric upon which every other joke will be measured. Holy shit. Oh my God. Nicole's hearing about this one, Dr. Harmon. Nicole's hearing about this.
I'm okay with that.
Every time there's something funny said in this class, I have to tell Nicole about it.
Why? She'll never stop talking to her.
Probably.
Or you'll just never talk to
Or
her.
you'll just never talk to
Or
her.
that's it.
One of the two. That's right.
That's no word.
Depends on how high your standards are. So dA is 1/2 r squared d theta is what we decided was the area of that little slice right there. And so we can divide by the little dt in which dA was swept out. So dA dt is equal to 1/2 r squared d theta dt. And then if we talk about resolving into VR and v theta, which you've had some inspiration in doing already. Now I know, yes. So v, of course, is tangent to the orbit at any point. And so we can resolve into parallel and perpendicular components to r. And so there's a, oops, if I drop perpendiculars in the r and theta directions, there's a component VR and a component v theta, and I'm going to decorate them with arrows because I'm thinking of them as vector projections, VR, v theta there. So v is VR plus v theta, which is VR r hat plus v theta theta hat. Yeah, you know, it occurs to me what's going on here is that since we started on Wednesdays, before I would have had another class that I'd already have taught. So in other words, I'm kind of like, wait, how come it's taken us to this point to get here, and then I just gave them this homework where they were using VR and v theta is because normally we would have had another class coming up, because we would start on Monday, and so there would have been a Tuesday in the first week, but there was only a Thursday in the first week.
We're behind.
What's that?
We're behind.
You're behind, so to speak, in a way, not really, but from that standpoint, yeah, well, we do have fewer classes now. What's that?
For the homework, we were behind.
Yes, it is true. But I relied on you to just read ahead as needed, and I'm sure you're such responsible that you did that. So that'll be r dot r hat plus r theta dot theta hat. Because, you know, if we did the E and M thing we were doing today, you'd have that dl was dr r hat plus r d theta theta hat, and then you just divide by dt to get that the velocity components are the r dt r hat plus r d theta dt theta hat, theta dot theta hat. So we can also say A dot is 1/2 r times r theta dot. We just got over there that A dot was 1/2 r squared theta dot. We call it dA dt and d theta dt, but we could also call them the dot notation. A dot is 1/2 r times r theta dot, or in other words, 1/2 r times v sub theta is what A dot is equal to. Theta is the component of the velocity in plane polar coordinates. Okay, any questions?
Comments, observations?
So r cross v in magnitude is equal to, v can be resolved into vr plus v theta, so it's r cross vr plus r cross v theta. But r cross vr is 0. R being the position vector, so r would be the vector that connects the focus, which we're taking to be the origin, to the instantaneous location of the planet, satellite, stranded astronaut, whatever is orbiting. So r cross vr is 0. Why that?
Because it's in the same.
Yeah, same direction, actually opposite directions,
Yeah.
but either way, 180 degrees also gives 0 cross product. Because they're parallel, that goes away. And then, meanwhile, Vr and V theta are perpendicular to one another. So when we're taking the magnitude, the sine of 90 degrees comes in, which is 1, so we just get r V theta for that result, since it's sine of 90 degrees, which so it's just r V theta. So, this says, but, I should say, but the magnitude of the angular momentum vector is going to be, well, the angular momentum is mu times r cross v. R cross mu v is the angular momentum of the reduced mass. So the magnitude of the angular momentum is mu times the magnitude of r cross v, which we just found to be r v theta. So the angular momentum is mu r v theta. Mu times r times the theta component, the not tangential, the perpendicular component of the velocity to the position vector. So r v theta is L over mu, or like L without an arrow on it, it just means the magnitude of the angular momentum. And thus we have that A dot is L over 2 mu, because A dot was half r v theta, but r v theta is L over mu, so A dot is L over 2 mu. which is what we were looking for. A dot is equal to L over 2 mu. Well, A dot is the rate at which area is being swept out. Does L change with time? L is the angular momentum. Is the angular momentum conserved or not conserved for our central force motion?
Conserved.
It is conserved. So L is a constant. Of course, mu is a constant also. So what this is saying is that the rate at which area is swept out is constant. Equal areas and equal times. That is Kepler's second law. So Kepler's second law really is a statement of conservation of angular momentum. That's really what it comes down to. Ooh. Ah. Since L is constant for a central force, we have A dot is constant, which implies the usual statement of Kepler's second law. So we have that equal areas are swept out in equal times. The rate at which area swept out is constant is the same thing as equal areas are swept out in equal times. Kepler's second law.
What a smart guy.
I know, except he didn't know it was the reason.
Um,
Newton was able to show that Kepler's second law follows from his law of gravity and laws of motion. Kepler just knew equal areas at equal times. He empirically deduced it without understanding the physical basis for it, which doesn't detract from the fact that he was a smart guy.
So did Kepler come before Newton?
Kepler came before Newton, yes. Newton came along later. At the end of the 1600s is when Newton came along and put the Y into Kepler's laws, which were formulated at the beginning of the 1600s. Yep.
History.
History, that's right.
That thing I've never.
All right, you know what? Because of the fact that this semester we are robbed of the first class, I'm going to go ahead and pull one of these numbers where I say, for interest and enlightenment, you should look in the notes at the very careful, it's in your book too, derivation of Kepler's first law. In other words, the proof that Newton's law of gravity combined with F equals ma implies that the orbit of the planet is an ellipse, or really the orbit of the reduced mass is an ellipse for the two-body problem, and therefore, big massive sun, cute little planet, you get essentially orbit is an ellipse with the sun in one focus. And you know, the good news is it actually makes use of the back minus cab rule, so that's exciting. You get to apply the back minus cab rule. Right? So, I will say, I highly recommend joyfully reading the proof. Of Kepler's first law in the book or my notes, which strangely enough are based on the book. Final result is that R is is L squared over mu squared over G times M times 1 plus E cosine theta is what you get for the equation of the orbit. And this implies that beyond that it could be an ellipse, that it could be any conic section, because this is in general the equation of conic section. So, we've already seen that for an ellipse, R is A times 1 minus E squared over 1 plus E cos theta. For 0 is less than or equal to E is less than 1. Or in other words, that it's some constant divided by 1 plus E cosine theta. This has that form, so this is telling us that if it's an ellipse, L squared over mu squared times GM is A times 1 minus E squared. So this has that form of an ellipse. If L squared over mu squared GM is bigger than 0, because 1 minus E squared is bigger than 0. For a parabola, parabola, for parabolas, right. Bolas always come in pairs. For a parabola, and the plural is bola, right? Yeah. For a parabola, what we find. Actually, when I was a little kid and I first encountered the word parabola in some book, I read it as parabola.
I think my brain thought that a parabola was a funnier way to say parabola.
Parabola.
So as a child, parabola, very mature.
Yeah.
It's a parabola.
Two p over 1 plus just plain cosine theta. So notice then we're saying that E is equal to 1 because the thing multiplies cosine theta down there, and that denominator is 1, and for a hyperbola,
Is there a hyperbola?
no, only hyperbolas. And in fact, that's the one case where you don't get a parabola is when one of them's so hyper that it just won't stick to the other one. That's a hyperbola.
Yeah.
This is really just degenerate.
It's only been about 20 minutes.
Yeah, I know. You think
It's because of that first one about Diego.
yeah. That's right.
I guess it's still uphill from that.
I guess.
Yeah. Because that was really at the bottom of the bowl.
You're really trying, aren't you?
Yes. That's for E being greater than 1. And notice that'll happen, that'll make A times E squared minus 1 be the thing that's positive. So in other words, what this is all saying is the orbit is a conic section. The orbit is a conic section.
You can have a hyperbolic orbit.
What's that?
You can.
Yeah, you can have a hyperbolic orbit. You can orbit on a hyperbola, which means it never comes back. You know, it whips around once and just leaves forever.
And my brain for some reason I saw like, oh, there it goes, and then it just flops right back.
Yeah, it only orbits on one nap of the parabola, of the hyperbola. It only moves on one of them. Yeah. So this is Kepler's first law generalized. retrospectively, I should have made this due on Thursday so that we would have had this class first. Was there anything you needed that, is there any reason to look them over again? Or did you get everything? So, okay. So now let's cover material that would be helpful to know for your first homework. Or let's put it this way. So now that you've done your first homework, it's helpful as we cover this material. Totally did that on purpose.
I mean, I think everything except for number 2 would have been fine.
Yeah. I mean, even number 2, I mean, it's as long as you know that R is whatever, it's what it comes from.
We just had to skip ahead.
I think it's more like-
So we got to the components and then we're fine. Except the math.
It's more like,
Well, yeah, it's the algebra. That's part.
it's like knowing in your heart you've seen it in class, you feel more like ready.
Yeah. Yeah.
And you're like, oh, what the hell is this? And you're just like, okay, well, I'll just do it then.
Yes. Well, I've already posted next week's homework, and we will have covered everything by then, because it's another chapter 2. And I plan to not be in chapter 2 by the end of the week.
Is that due Thursday?
No, it's due Tuesday, because I'm trying to avoid crunched E&M and ASTR at the end of the week. So
Appreciate that.
we could, I could just make them both due on Friday, and then you could decide you're going to finish the astrophysics by Tuesday, but I know how the actual world works,
Yeah.
which would mean you'd still end up, oh man, God, I got 2 assignments due tomorrow,
I'm
so
going to die.
I don't want to give you enough rope to hang yourself. So,
That's why I always joke that the physics department's on the basement floor. It's because you have to walk all the way up the steps to jump off. It takes all the way up there before you.
right, yeah.
I'm trying to turn back.
It won't make it easy.
Yeah. Right, yes. Well, do you know the reference of enough rope to hang yourself?
I know what it means, yeah.
Basically, the communists said that the capitalists would sell them the rope
Oh.
that they used to hang themselves. Yeah.
Not wrong, but.
Perihelion and aphelion. Or in general, at the ends of the major axis, because we're not going around the sun, it's not aphelion and perihelion anymore, but you know what I mean. In that case, the position vector and the velocity vector are perpendicular. Because it's moving always tangent to the orbit, and so perihelion and aphelion, where it's swinging around the bend at the end of the major axis, it's moving perpendicular to the line from the planet to the sun. So there's R at aphelion and R at perihelion. So here's V at aphelion, R at aphelion, R at perihelion, V at perihelion. They're perpendicular in that case. So L equals mu R d theta becomes L equals mu RV, since V is V theta at both of those times. There is no radial component at both of those times. VR is 0, so it's just mu RV at aphelion and perihelion. So at perihelion, R sub P will be using that result over there, L squared over mu squared times GM over 1 plus E cos theta. Oh, and I've silly. So what I forgot to write down is this implies, as you used in homework because you were so well prepared for it by lecture, that L is the square is mu. Did we already do that or not? I can't remember before. Is this? Yeah, okay, so, right. L is mu times the square root of GM times A times L is the square root of mu, is mu times the square root of GMA 1 minus E squared, just solving for L in that equation right there. Whoops, no, I didn't do it yet, okay. Let me fix this, I forgot to do this just before. Well, at least it's going to be on video forever, okay. So if we use these expressions here, so for the ellipse, what's that?
So they don't have any reason.
Don't have an eraser. I can teach you one.
No, it's okay. I'll use this now.
For the ellipse, this does L squared over mu squared times GM is A times 1 minus E squared.
Really?
So now, we just solve for L. L equals what I was writing before, mu times the square root of GMA times 1 minus E squared. Boom.
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 It'd be really funny if there was like a catalog of all the things that famous physicists and mathematicians said after they reached like some really integral, like fundamental thing.
Yes.
It's like, what did they say? It's like, huh, hold on, dang. Ooh.
I totally was not expecting that.
Just like, I don't get it.
Oh well, so much for physics.
Take that, science.
Yes.
A lot of the 1600s was like, wow, the church isn't gonna like this.
Yeah. Wow, look at that. The world's going to end in 2012.
That's what the asterisks are thinking, like, oh,
Yes.
shit.
Uh-huh. Because if you run out of calendar, obviously you can't continue to exist past it.
Of course not.
Of course not.
There's any movie about it. Of course it's true.
Yes. Uh-huh. So,
Survive your delay.
so plugging into the perihelion, this is L as mu R perihelion V perihelion. You get mu RPVP squared over mu squared over GM times 1 plus E, because cosine theta is equal to 0 at perihelion. Remember, theta is angle away from perihelion in the polar coordinates equation. So now we can solve for the perihelion velocity. That says that Vp squared is Gm times 1 plus E divided by Rp. Which is Gm over A times the quantity 1 plus E over 1 minus E, using the fact that Rp is A times 1 minus E, as we found some time ago. Perihelion distance is the semi-major axis times 1 minus the eccentricity. And that's box-worthy. That's the perihelion speed.
Neutral mass.
Yes. That's the whee! Yes. In the whee! That's one is the, all right. And in fact, if you do the same thing for aphelion, all you do is flip the numerator and denominator over there. So similarly, the A squared is equal to GM over A times 1 minus E over 1 plus E, instead of 1 plus E over 1 minus E. So nice simple expressions for the perihelion and aphelion speeds. Notice that'll be smaller because this time you put the small thing on top and the big thing on the bottom, whereas in the other one it's the other way around. So what's the speed for a circular orbit? Equal to, what does this formula say the speed is for a circular orbit? GM over A, square root, right, because it's B squared, because E is 0 for a circle. So for a circle, this gives you the circular velocity being root GM over A, which is right. Okay, any questions?
So that would imply that a circle doesn't have a perihelion?
Every point is perihelion and every point is aphelion for a circle because you're always the same distance away.
Yeah.
And every diameter is a semi-major axis for a circle because it's a special case. So it's special. That's right. It's spatial too. The total orbital energy is E equals kinetic energy, 1/2 mu V perihelion squared minus potential energy minus Gm mu over R perihelion. Remember, the energy is constant, so I can plug in any point along the orbit, and it'll always be the same as it is there. So let's just use perihelion, 1/2 mu perihelion. The kinetic energy of perihelion is 1/2 mu V perihelion squared. The potential energy is minus Gm mu over R perihelion. I can also plug in an aphelion or anywhere in between. It's fine, but we know values for perihelion, so we'll plug in for perihelion to do it just as well for aphelion. So that's going to be 1/2 mu times, well, V perihelion squared is that expression over there. So Gm over A times 1 plus E over 1 minus E. And we know the perihelion distance is A times 1 minus E, so we can put that in, minus Gm mu over A times 1 minus E. So let's factor Gm mu over 2A out. Because both terms have Gm mu over A. The second one has just Gm mu over A. The first one has a half in it, so let's pull that out too, which means we'll need a factor of 2 of the second term. So this will be times 1 plus E over 1 minus E, and then we'll be subtracting 2 over 1 minus E, because we need a 2 to cancel the 2 from that second term. And now we've got them over a common denominator. Denominator. It's devilish on the bottom, I guess it's a denominator. AO. So I get to subtract 1 plus E minus 2 is E minus 1, which I'm going to write as minus, I'm sorry, it's, where am I? Yeah, it's E minus 1, which is minus 1 minus E, which will cancel that on the bottom there. So this all simplifies, in other words, to minus 1. So I just get minus g m mu over 2a, because what's in parentheses is equal to minus 1. 1 plus e minus 2 is e minus 1. E minus 1 over 1 minus e is minus 1, because e minus 1 is minus 1 minus e. So that's lovely, because that gives us a nice, easy expression for the total energy of the orbit. We've derived it at aphelion, but the energy is constant, so it's true at all times that the energy is simply minus g times m mu over 2a. But remember that m mu is m1, m2. Also, in other words, minus g m1, m2 divided by a. If you don't believe it, m mu, what's m? Big M, in terms of m1 and m2, the actual two bodies involved. M is m1 plus m2, it's the system mass. Mu is,
M1 plus M2 over M1, M2?
it needs to have units of mass, so that would not. Right? Yeah, it's got to be m1, m2 over m1 plus m2 to have units of mass, to have the right units. So if you forget which one's on top, think units. So the m1 plus m2s cancel, and you're just left with m1, m2. So big M times mu is m1 times m2. Which you can always keep deriving, or you just remember the product stays the same. Yes?
So, where'd the 2 go?
What two?
Let's do
In the
it.
technology,
It didn't go anywhere. It stayed there. I just forgot to write it. Thank you.
Okay.
Yes.
Speaking of 2s, where
Yes.
on the bottom part, where did the 2 over 1 minus e, where did that 2 come from?
Because if you look over here, gm mu over 2a times 2 over 1 minus e will make the 2's cancel so that this term results, right? I factored out gm mu over 2a. This term doesn't have a 2 in it, so I need to add a 2 to it, or multiply it by a 2, in order to compensate for that division by 2 when I factor it out.
I see. I see, so the line
Okay, happy? Happy, happy, happy. Happy, everybody not happy?
I'm totally unhappy.
So, what does this say? It says, for a given pair of masses, the energy depends entirely on the value of A. It's the only thing that matters. So only the size of the orbit is important, not the shape of the orbit in determining the energy. There's no eccentricity in there. All orbits of a given, for a given pair of masses, all orbits of a given A have the same energy. Remembering again that A is the sum of the two semi-major axes of the two orbits. Semi-major axis of the relative orbit. And furthermore, there's something profound that we can realize here, which is pretty cool. Note that from the fact that the orbital angular momentum is mu times the square root of gm times a times 1 minus e squared. So note the angular momentum does depend on the x for a given value of A, and thus E, the maximum value of L corresponds to a circular orbit. In other words, of all the orbits with a given amount of energy, the circular orbit is the one that has the largest angular momentum. And I like to kind of illustrate that by drawing. Remember that the semi-major axis determines the energy, so there's the major axis, half that would be the semi-major axis. And I could draw various ellipses that have that semi-major axis. So I could draw a whole family, an infinite number of ellipses that are less and less flattened. And the least possible flattening is the circle. So there's a whole family of orbits, and the one with the highest angular momentum is the circular orbit. All these orbits have the same energy, but differing angular momentum. Same energy but different L values, and the circular one is the max for L. There's the sun. There's the planet of doom. There's the orbit of the planet of doom. You can see why I'm calling it the planet of doom. It's just going to land inside the sun. I'm literally saying it falls straight into the sun. That is one orbit, right? It falls straight into the sun. What's its angular momentum?
0, 0.
0, because it's moving straight in, so it's always r cross p is 0. So it kind of makes sense, right? The straight line fall into the sun planet of doom orbit has no angular momentum. And as you get more and more elliptical, more and more circular, so to speak. So in other words, you start becoming ellipses that move towards circularity. You're getting higher and higher angular momentum up to a maximum value for the circular orbit. Yes?
So that would mean that a line doesn't have a semi-major axis, which makes sense.
Yeah, it's so. If you think of the elliptical orbits, the foci, where are the foci for the circular orbit?
At the center.
At the center. And as you keep moving the foci further and further apart, the eccentricity gets bigger and bigger, right? The maximum eccentricity would be 1, where the foci in that limit would be at the ends of the major axis of the orbit, because remember, the eccentricity is the ratio of distance from center to focus divided by semi-major axis. So in the limit for elliptical orbits as e approaches 1, we know that e is 1 is a parabola, but the limit that the elliptical orbits are approaching is a line segment. And this is the line segment orbit that they're approaching, that the aphelion velocity is 0, and if the aphelion velocity is 0, if you just let go, it's going to fall straight into the sun. And that would be 0 angular momentum in that case. That's the planet of doom orbit. But if at aphelion you give it even a little bit of kick sideways, then it's on an elliptic orbit. Well, if hit the surface, the sun's not a point target, but ignoring that complication. All right, break time.